Okay. So last class we covered we discussed complete randomized experiment, and so yeah. Okay. So the Neumann theorem developed design-based inference, but the variance estimator overestimate is conservative in the sense that it overestimate the true variance, true design variance. But if you use a superpopulation model and apply two-phased framework, then you can actually achieve the obtain the variance. So you have extra term. So this one is the extra variance due to the randomness from the phase one sample, right? So and then that implies your target parameter for variance estimation is this guy. So this is what you want to estimate. And then the only unknown parameter is a sigma 1 square and sigma 2 square, sigma 0 square. So you can use the property of a simple random sampling. So basically, this is sample variance. So sample version of S square. And then this is essentially so this is 1 and 2, right? So phase 1 and phase 2. So phase 2 is a simple random sampling essentially. So we know in our previous lecture we have already shown that sigma 1 hat square is unbiased. So that's what you get. And then under the IID realization, sigma square is unbiased to sigma square. So we get so that means we S1 hat square is unbiased estimator for sigma 1 square. Similarly, S0 hat square is unbiased for those sigma 0 square. So the unbiased variance estimator can be obtained like this, which is not surprising because we because if you have a two-phase, so this is IID and this is simple random sampling, then this one, end of the day, this is actually you can treat it as IID. So then implies, so this property implies that they are unbiased, right? Okay. Now here's another interpretation. So rather than using the potential outcome, you can directly use the observed data and estimate the parameter using regression. So we already discussed this, right? If you just apply regression of y on TI, ordinary least square method, will actually the slope estimate time, right? So slope is equal to difference in means estimator. So that we show this already. So now next question is how to compute the variance. So how to estimate the variance of this estimated regression coefficient. Well, you can so using the matrix notation. So I hope that you guys probably understand what I'm talking about when I write it this way, right? So using the matrix notation, we can write the OLS estimator as something like this. And then you can the error term can be written as so then the error term can be written as, so this is E. So you can get this. And EI is a random variable. So conditional on X, the variance is X prime X inverse, variance of this guy, and X prime, right? So, well, if you are not really familiar with this, then you can understand it as so X is a vector, right? P-dimensional vector. So then X prime is a P by P matrix. So you sum over them is still P by P. So so that's why this one is equal to this one. This guy is equal to this one. And this guy is actually can be written as I equal to 1 to n, xi, and then ei. So this is a column vector. Ei is a scalar, but xi is a vector. So then the variance of this guy, so variance of this guy is a xi prime over variance of ei, right? Because we assume that independence. So we get this. So then the variance of ei can be estimated by ei squared if you observe it. But if you don't observe it, you just plug in by residue. So that is the typical formula. So that is sandwich variance formula sometimes. That is sometimes called sandwich variance formula. Okay. So I just want to make the connection with this formula. So how we can interpret this formula to this problem, right? So then basically this is our xi prime. So x is now two-dimensional vector. So then you can basically, so this is our x. But this is not really convenient because these two columns are not orthogonal. So maybe a better way is to use orthogonalization. So these two, if you write this way, so so basically prediction, okay? So this prediction which is, does not change with the linear, as long as the basis functions are the same, right? If the column, so if you write it this way, so let me write it. The head is x prime x inverse x prime y, where gamma head is c prime c inverse c prime y. Okay. So the first line is a prediction using x vector, while the second one is a prediction, linear prediction using z. So now the question is, when this prediction and this prediction are equal, okay, it is equal if the column space of x is the same as column space of z. So you can basically, the point is that you can express the linear combination of this guy as another linear combination of these two guys, right? So you can write A1 plus B Ti can be written as A prime 1 minus Ti plus B prime Ti. So if you can find, given A and B, if you can find P prime and A prime to satisfy this, then it means that they are in the same column space. Okay. Here you can, of course, you can find it, right? So how? Because you know that A prime is A and P prime is P minus A. So you found it, right? So that means they are indeed same, spans the same column space. That means they both can explain the same thing as a linear combination. So long story short, instead of using this column, right? Instead of using this basis function, I like to use this basis function. Why? Because if you use that, then x prime, x prime is a diagonal, right? Because they are orthogonal. So they are orthogonal, so they are diagonal. So the inverse is easy to compute, right? 2 by 2. Well, computing the 2 by 2 matrix is not difficult anyway, but even, right? We want to make it even easier. So then basically, so if you, okay, if you use that, what is the x prime x? X prime x is a summation of okay, 1 minus ti 1 minus ti, right? 2 by 2 matrix. So that is actually summation of 2 by 2 matrix with basically summation of ti 1 minus ti square. 1 minus ti square is 1 minus ti, right? Because they are either 0 or 1. So then is actually n0, 0, 0, and 1. So you get, that's why you get this one. So because you have x1, x prime, x inverse, both sides, right? You have this term, two terms, both sides. So you get n1, n0, n0 and 1 squared, inverse squared. And then the next thing is to compute this guy, right? Compute this guy, which is basically computing the residual squares in the when t equals 0, and the other one is t equals 1. Sum them up. So you can check that this one is actually indeed x prime. So these two indeed corresponds to computing x. So computing the summation of xi prime, the i's hat square. Okay. So then you get eventually obtain using the covariance matrix, you eventually get this. So this one comes from the equivalence, right? So this is a previous page, page 22. So this equality comes from the result from page 22. This equality comes from the result here. we use the result here. It's always important to understand whether this each statement is an assumption or a result of your assumption, right? Or property. So so whether it's a derived or whether this is what you start with, right? I mean, so to be clear, that's probably the first step in the critical thinking. So anyway, so end of the day, basically, the point is that this sandwich variance formula gives you basically the same variance estimator asymptotically. So that is all about section part 1 lecture. So I'm gonna move on to today's part 2 lecture. So now we go back to sampling. So we studied the simple sampling. Now we move on to stratified sampling. So stratified sampling is really a popular technique. So we first partition the population into mutually exclusive and exhaustive subpopulation. So exclusive means what? Exclusive means that the union, right? Union covers the population. So that is a meaning of the exclusive. Oh, no, sorry, the other way. Exclusive means that there's no intersection, right? I mean, the intersection is empty set. So that is the exclusive. Exhaustive means that it is actually union of the clusters or a population, subpopulation, covers the population. Okay. So that's basically the first part is about the partition, the nature of the partition. The second part is about the probability structure, the sampling structure. So what we select from one stratum is independent of your sample selection to the other stratum. Okay. So if I belongs to H stratum, J belongs to G stratum, then the probability of selection in for different stratum are independent. Okay. So that is the very nature of the stratified sampling. And one particular example, one special example is stratified random sampling. So stratified random sampling means that stratification plus simple random sampling within each stratum. So basically, stratification is a step 1. Simple random sampling within step 3, right? But when you do simple random sampling, you implicitly assume that sample size is known, right? Sample size is given. So that means we need to determine sample size, first of all, before we do simple random sampling in each stratum, right? So then that is actually a additional topic in stratified random sampling, because you need to first determine sample size for each stratum. So that is actually for H, right? For each stratum, you need to determine NH somehow. And then given NH, then you can basically carry out a simple random sampling independently. So that part is easy because we know what simple random sampling is. So that part is easy. Okay. So determining a sample NH sample size in the context of stratified sampling is especially called sample size allocation problem. Okay. So sample size allocation problem is N is known usually given. N is like we have a budget, right? Then we know that we want to use select 1,000 sample, for example. But what we don't know is how to allocate. So this is a given, but then N1 plus NH. So is to be determined, right? To be determined. And so a sample size allocation problem. Right. Okay. So why? So why we are doing this? Well, several reasons. Control for domain of study. So, for example, if you are doing agricultural survey, right? If you are interested in, estimating the crop acres for each crop and something like that. So in Iowa, what is the total acres of land used for corn, right? Cropping corn, something like that. So that is supposed we are interested in this kind of statistic. We so then the government USDA could be interested in the total amount in the US, right? Total acres in the US, as well as the acres in each state, right? So then the domain. So control the domain of study means that it's not necessarily, it's not only the national level, but also you are interested in a state level, right? You could be interested in state level. Then you want to maybe allocate certain amount of sample size to control. So control means that you want to make sure, for example, at least 50 sample within each state, something like that. Otherwise, if you just do simple random sampling over the whole United States, by random chance, Iowa may not end up having no samples, right? That's not good, right? So then we want to control certain precision. So we want to make sure that certain minimum number of samples are selected for each stratum. So that is a practically quite important issue. And also flexibility in design and estimation. So maybe the natures in Iowa could be quite different from the natures in Alaska, right? And so then if you stick to the same sampling design for different state, maybe the implementation could be difficult. So we want to have some flexibility. So we basically want to stratify first, and then each stratum we treat them as a separate population, and then we try to each state office knows better, right, about how to collect sample, and so we can actually be have some flexibility in the actual implementation. Convenience, of course, I don't exactly know what convenience means, but I think it's maybe related to flexibility and efficiency. So efficiency means that efficiency in terms of statistical efficiency, in the sense that variance is if you stratify. So first of all, stratified sampling itself does not necessarily decrease the variance. If you make a very poor stratification, you could actually increase the variance. But if you have a reasonable, sampling, if you have a reasonable stratification strategy, like stratified well, and then a sample size or location was made properly, then variance will be reduced. Variance with variance of the Hurwitz-Thompson estimator. So to be more rigorous, variance of the Hurwitz-Thompson estimator on the stratified random sampling will be smaller than the variance of Hurwitz-Thompson estimator, on the simple random sampling, given the same sample size. So to make the comparison fair, we want to use the same sample size, right? Given the sample size, well designed stratified sampling can reduce the variance. Okay. If you remember the toy example in the very first class, like 4 farms, 1, 2, 3, 4. Yeah. So if you remember correctly, the first 3 farms are relatively small size, and the last one is bigger one. So it makes sense. So rather than 2 sampling designs are introduced. First one was a simple sampling, and second one is selecting one from the 3, and the other select another one from 4, right? So this one is a special case of the stratified sampling design, because we stratify the farm into 2 groups, and then we do sample selection within each street. Okay.
And the assumption of the variation across like what about the length? Is there any assumption about the variation?
Yeah, that's a good question. So I will cover that soon. So when I say that efficient sampling design, I mean sampling design should be good. So what do I mean by good, right? So that means within the stratum, Y values are relatively homogeneous. But between stratum, they are more heterogeneous. Then it can be regarded as a good sampling, good stratification. So that part will cover. We'll see soon. Okay. Yeah. Good question. So this is pretty much obvious in some sense, because we know that total. I mean, we know that the parameter, right? So this is a parameter. So capital Y is a population total. Oh, Y, of course. So Y is a particular size variable, and then this is a parameter basically, finite population parameter. But then this guy is what? Total of Y in stratum. Yeah, okay. Stratum H, right? So basically we, stratified sampling, we kind of stratify the population. So then each stratum, so total is essentially can be written as a summation of the subpopulation totals. So then total estimator could be some of the subpopulation total estimators, right? So that's basically what it is. And then variance. And then from here, right? From here, variance of originally is variance of H, Y hat H. And then to be rigorous, this is actually, you can, in general, you can write it this way. right? So your Hurwitz Thompson estimator is can be expressed as a summation of the subpopulation, summation of the Hurwitz Thompson estimators in each, right, in each stratum. So it's a summation. And then how to compute the variance of this guy? Well, it's a linear, so you can basically, variance of the summation is a summation of the variance, and then double summation of the covariance over two different, right, H and J, G. But the covariance for H not equal to J is 0. Why? Because of the second property of the, so if you recall that stratified sampling, the second property, this one particular implication of the second property is that covariance of Y hat Hurwitz Thompson and Y hat G Hurwitz Thompson is 0. H not equal to G, right? Because of the independence, the how you the randomness here are totally different from independent of the randomness here. So they are actually independent. The covariance is 0. So that basically we don't have to worry about this double summation. So then the variance is written as a sum of the variances in the subpopulation. Then of course, once you accept this relationship, then you can obtain. I think maybe I'll, yeah. Okay. Yeah. We can, of course, we can, as long as we can get constant variance system, unbiased variance estimator, then you can use it as a total variance estimator. Okay, so that's for the general, right? For the general stratified random sampling, stratified sampling design, and then for the special case of a stratified random sampling, which means that you have a simple random sampling within each stratum, then you have a so this is a kind of a Hurwitz Thompson estimator, Hurwitz Thompson estimator in H, right? So Hurwitz Thompson estimator or the subpopulation H total. So so then of course this one is also the same story, right? This is variance of the Y hat Hurwitz Thompson. And I used the variance formula for simple random sampling. And then here, the only difference is that I use, so this capital S square is replaced by small s square because on the simpler sampling, small s square estimate the capital S square unbiased. Okay. So that is pretty much the basic. And then now we focus on choosing the sample size. So within each stratum. So sample size allocation problem is that given the total sample size, right? Given the total sample size, how to choose NH? And yeah, maybe so this is two popular method. One is the proportional allocation, which basically use the bigger population, we just allocate more proportionally. And optimal allocation, we we use some statistical, optimization problem. So we have a constraint that we have a sample cost function is given, and then we want to use some criteria to find the NH. So this optimal location is first proposed by Neyman. So this Neyman is the same Neyman, okay, in the causal inference. So the Neyman in causal inference was at that time he was in Poland. So he was a Jewish in Poland, and so he got his PhD at university in Poland. And then later he moved to Berkeley, UC Berkeley. So he became a chair in a UC Berkeley in the statistics department, and so he wrote this paper. I think this is 1972, something like that. So he's the father of causal inference and also survey sampling. Okay. So that we'll see this soon, but we'll first focus on proportional location. So the concept is really easy, right? I mean, just the proportional location is the sampling. So this is the proportional location. The proportion of sample size in particular H is equal to the proportion of the population size, right? In that industry. So one implication, so that is okay. The first one is that all weights are equal. What do you mean by that? Let's take a look at the formula here. So if I write it, okay, as a sample, I mean the weight, AHWIYI. Okay, if I write it, if I express the whole thing as a linear function of weighted sum of the y in the sample, okay, then if I write it, then that means Wi is what? Wi is NH divided by small nh, right? For I equal AH. So this weight we use for stratified random sampling is NH, capital NH divided by small nh, which makes sense because how many population element does the sample for each element in sample represent, right? So okay, so suppose weight is 100. That means what? That element represent 100 elements in the population, right? In this example, for example, this guy, if after you compute this one, you multiply 3. But here you have a sampled element. If you choose 1, if suppose you choose end up choosing first element out of 3, that means this y1 actually represent the others too, right? So it should have a weight 3, but this one is always 1 times 1 because it only represents itself, right? I mean itself, nothing else. So Okay, because we our selection is selecting from, you know, select the NH from NH with the equal probability. So that means the weight should be capital NH divided by small nh, right? But on the proportional location, okay, on the proportional location, what does that mean? So this one implies that nh divided by small nh is equal to n divided by n, right? So that means your weights are all equal. So this is so the left side is actually weight on the STR in general, right? The weight that we use, the left side, is a weight on the STR in general. But in the special case of the proportional location, the weights are all equal. So that's actually quite attractive because it's very hard to make a mistake, right? If the weights are all equal, then you know, if even if you have a weights are all equal, and then maybe someone in the government office who does not really know how to use how don't know much about sampling, maybe get confused. But if you use just the equal weight, then it's the easiest possible thing, right? So practically quite attractive in that sense. And secondly, you get some variance formula simplification. So let's see proof of one. So variance of Horopi-Thompson in general on the stratified sampling. Okay. And then on the proportional location, right? On the proportional location, we have this property. So that means on the proportional location, we can actually have n oops, there's no okay. And then what we want to compare, okay. So you could, another way of writing is an H right this way, and then in equation one we use this one is an H. So same thing. And then what we want to compare with is sorry, I should. fresh air. So on the simple sampling, remember what on the simple sampling, we have a same very similar formula. The only difference is that we have a s square. So you can compare this one with this one. The other factors are all the same, right? The only difference is this. And now, what should we do then? Well, maybe you can write it as a like this: 1/n-1, h equal to 1 to h, I equal to UH, yi minus y bar square. So that is actually 1/n-1 SST. Sum of square total. So I'm trying to do ANOVA decomposition. This one, you can write it as a okay. What am I doing? Well, right, we can, sorry, we can move we can move 1/n outside, and then to h, and then yi minus y bar h square times n h divided by nh minus 1. I should write it, maybe I should write it smaller or make it bigger. So let me write it again. UH. Let's write it this way. Oops. NH minus 1 UH yi minus y bar h square. Okay. So that is actually, if you can equal to, approximately equal to 1 if NH is large. Okay. So if NH is large, then you can ignore. Then you end up writing it as, oops, my, okay. You can write it as, write it one more time. Okay. So the nature of the stratified sampling, you have SST, total sum of square component. While in nature of the stratified sampling, you end up getting within variability. You don't have to worry about the between. Okay. So that means if you compare this with this, right? So if you compare this, SST is greater than or equal to, right? So this one is bigger than this one. So that means the variance on the product terms is on the stratified sampling, stratified sampling will be smaller than than the variance on the simple sampling. If the sample size allocation is proportional, okay, on the proportional allocation. So that is the advantage, big advantage of proportional allocation. You are guaranteed to achieve the efficiency gain using stratified sampling if you use proportional allocation. So the caveat is that this result does not mean that stratification is always better than sequence sampling, because if you use very bad sample size allocation, if you use very poor sample size allocation, actually you can make it worse. So this is one thing. Now the next topic is then what's the best way, right? So optimal allocation. So sample size. So we can we have sample size allocation. So two problems actually: sample size allocation, and then also what is the total sample size that we want to use. Well, the second problem is more has to do with the total budget or total accuracy, right? So total budget, so depends on your budget, right? If you have a lot of money, then you can maybe you want to select more, right? But or another way is if you have a specific margin of error, so the measure of accuracy, then you want to use that as a kind of a standard to determine your sample size. Okay. So let's formulate the problem. Given the budget, known population parameters, we wish to find the sample allocation that minimize the variance, subject to the constraint that the total constraint cost is C less than C. Okay. So what I mean, how to construct the cost function? Well, to think about designing a survey, right, using a simple stratified random sampling, then when you design a survey, you first create the questions, right? You create the questionnaires, and maybe do some, test before you do the real survey. And also you may want to, store the file, and so these are, so initial cost has nothing to do with the sample size. Okay, even if you end up selecting none, there's a cost, initial cost always. I mean, if you spend time, right, then on this project, your labor is a cost, right? So that is the initial cost. And then this one is more like a observation cost, means that when we ask questions to interview, then there's some labor, right? We can hire interviewer, or we can also give some incentive, right? So if I suppose I give a Starbucks coupon, $10 Starbucks coupon for as a compensate for your interview, right? I mean, then these are the costs, right? So that is actually proportional to the sample size. So this is more like a reasonable cost, and then maybe the cost could be different for different areas. Like California, maybe the living cost is high, so higher than Iowa, right? Then maybe California, you maybe the labor will be more expensive than Iowa, something like that. So that could considered in the cost function, and then the objective function, right? The objective function in the optimization could be it can be written as this one, right? So this is your so this part is already result of our calculation here. So this is the formula, right? This is formula on the stratified random sampling, and then you can expand to you have this guy, so you expand, and then first term and second term you have some cancellation. So the second term turns out to be free of sample size. So second term is just a constant, free of NH. You don't have to worry about that, right? So your actual because so they are basically this is all given, and the only thing to be determined is this one. So how to solve this kind of problem? Well, so minimize subject to constant. So this is your mathematical formulation of your optimization problem. So everything else is constant, right? So CI, NH, SH square, and CH are all known here, given. What you want to determine is only NH. There's some prayer. I don't remember exactly. We, uh, we can accept the known given and then control on the well what never mind. I will let you know. So anyway, critical part is whether what is under our control, what are not under our control, right? So that is the key part of the living a peaceful life. So we really want to control. So NH is only under our control. Then idea is there's a many different ways, but I like to use maybe Cauchy-Schwarz. This is turns out to be very powerful formula, right? And you have a this is a kind of Cauchy-Schwarz or sometimes Schwarz inequality. So here basically I want to use this one, right? And then this side is n. So then you actually have a sorry, Cn, right? So because this is constant, so constraint. So this is not really okay. Let's write it again. CHNH. Okay. But anyway, we still get constant in the sense that free of. So we can, this is what we want to minimize, right? Minimize. So then we know. So all we have to do is where this equality. So with equality, okay, if and only if, when here with equality, if and only if AH is proportional to BH, right? So we want to use that property. So that means NH, SH, NH is proportional to CH square root of, oops, NH. Because this is our AH square, right? And this is our BH square. So that means this statement is equivalent to this statement. So then NH, SH, so you can move NH here and SH denominator. That leads to this result. Okay. Okay. So let me, whether there's a, okay. So that basically is a mathematical, derivation of the result, Neumann. So this is a formula for Neumann allocation. Yeah, Neumann allocation. And let's try to interpret what it means. So if NH is large, then we should increase the sample size, right? So if the particular stratum has a lot, many elements, right? Then it makes sense to, give more sample size to that stratum. If SH is large, that means the stratum, particular stratum has more variability, right? More variability. Then it's better to use more resources more samples to control the variability. So the second part. And also, if the cost is high for that particular, say that stratum is Alaska, right? Then maybe the cost will be higher, right? You have to fly there and something like that. So then maybe you want to reduce the cost. And another interesting part is that if we don't know, right? SH is actually population variant, I mean standard deviation. So there's a population characteristic, so which we may not know in advance, right? Then suppose you have no information about that, then maybe you can just assume that they are all equal. In that case, it becomes a proportional location, right? Because this SH cancels. So that in that sense, proportional allocation is not really bad. And secondly, if you compare, so which one will be, so you have a proportional allocation and Neumann allocation, and which one will have a smaller variance? Well, in some sense, by definition, right? Because we already optimize right? We already try to minimize the variance. So if you ignore, right? If you don't know, if you assume that the costs are equal, right? Costs are the same, then our problem is just minimizing the variance. And then proportional location actually belongs to that class, the same stratified estimator. So that means this is kind of trivial by definition of the optimal, because this one achieves the minimum variance in the class of stratified by the sampling anyway, right? And but you can actually carry out some algebra, uh, and check that the variance user. So if you basically you compare this one with this one. With this one. So this is if you this is a kind of a weight square and it's a square of so weighted at square. So this is more like a expectation over x square, and this is more like a expectation x square, right? So that means Jensen's using the Jensen's inequality. This is big, right? Okay. I like to use some use the let me stop share. Okay. And then stop use a screen share here. And example. Okay. Huh? What's going on? We should have a okay. So this is R markdown. This one. So if I need okay. Is it big enough or okay. So I have some this is actually real data. And so you have a US agricultural census. So census of household and population takes every 10 years. But agricultural census, they have every 5 years. So we have at that time, we have so the data set. So this is the data set has a discount. So each unit is a county. And then county can be classified into four regions, right? Northeast, northwest, central, south, and west. So we can treat it as a stratum. And then, so in population, northeast, north central, Iowa in north central, right? And then south and west, we have these kind of counties. So this is basically just a few lines of each data. So and then if V15 region is northeast, I make pop one, and the pop two. So basically, this is stratification. And then proportional location. So proportional, if I do, so my sample size, total sample size is 300. So I have a, I like to use a 300, allocate 300 sample size to 4 regions. And the first step is just to use proportional allocation, right? So if I do proportional allocation, I will skip all these, but point is, okay. We can read. So okay, so this is variance you would get using proportional allocation, and this variance compared with simpler sampling. So this the ratio of the variance of stratified random sampling over simpler sampling is about 82%, which so variance is go down, right? By using the proportional allocation. But this doesn't seem to be a lot. But anyway, and part of the reason is probably is that straight and four. If you look at the straight and four, this variance is actually 15, right? Power 15, the other is 14. So this variance is high. So even though the population size is not really high, right? So this, what is the four? Four is west. Okay. Yeah, so west, yeah, west straight up somehow, I think west stratum maybe counties has a bigger size, and then maybe the variation of the crop acres could be more very highly variable than northeast. Northeast in the developed first, right? So they have more counties and so anyway. Now let's try optimal location. So this is what I like to show. So let's try optimal location. If you do that, then this is your result, 2.83. And so the variance reduction due to optimal location over proportional location is 0.67. So which is quite a good big reduction, right? You have the same stratification, you only change the sample size. I mean, total sample size is the same, right? So if you allocate your resources cleverly, you gain a lot. Actually, the gain is higher than the gain from over sampling, right? So that I thought is quite interesting. You guys can take a look, and if you are interested, and this is all for today. Okay. And homework is due tonight, so